design based on the transfer function approach, what we know as classical control. And the second one is based on what is called as a state space representation, right? Which we will look at it from the next class, right? So what I will do, Prem, is that like first let me complete the material which is for today's class, and then I will give a brief overview of where we are till now, right? The big picture.
Sure, sir. Got it. Yes.
Right? Yeah. Okay. So if we look at where we stopped yesterday, we were looking at the what to say Bode diagram, and we stopped here. So please note when you come here this Sunday, kindly submit homework 1 to 3, and I have also discussed with Abhinav, who's the TA. He will also be there, so that you can meet him in person. And please submit the hard copy of assignments 1, 2, and 3. Okay, when you come. Okay. Then we will what we will do is that like we will essentially initiate the projects for the books. Okay, so because that is going to be important. So we shall initiate the projects for this particular course from next week onwards. Okay, but we will discuss more when we meet on Sunday. Okay.
Right.
So yeah. So in addition to the Bode plot, I just wanted to briefly tell you what the Nyquist plot was, but we are not going to go in depth into that. So the Nyquist plot is essentially plotting P of j omega, but instead of magnitude and phase, we plot the real part and the imaginary part. Okay, as omega is varying. All right. So essentially, we essentially plot the real part of the sinusoidal transfer function and the imaginary part of the sinusoidal transfer function as we vary the frequency omega, right? So that is the Nyquist plot, but yeah, so it is NPTEL videos, but I am not going to go into that because for the purpose of automotive control, it is an important theory to learn, but then the applicability it has been minimal, right? To the best of my knowledge. Okay, so that is why I'm choosing concepts which are relevant to our course. So that's why I'm moving forward. The next important concept is what is called as relative stability. So what is this relative stability? So if you recall where we started, we had this basic closed loop control system, right? Where G of S was the forward part transfer function. So G of S was C of S times P of S, the controller transfer function times the plant transfer function. And the closed loop transfer function, we can get it as G of S divided by 1 plus G of S H of S. Okay. So that's what happened with the closed loop transfer function. We are already aware of that. And the closed loop characteristic equation is 1 plus G of S H of S equals 0. So now, if you plot the S plane, right, and we know that the S plane is divided into the LHP and the RHP. Suppose, let us say we consider two systems. Okay, so we consider system S1, whose poles are at this location, and then we consider system S2, whose poles are here. Okay, then if we look at system S1 and S2, both systems are stable, right? Because as we immediately realize, for both systems, the poles are in the left of complex. Okay, so stability is assured. But now, as we know, this entire theory that we have been learning is based on approximations. That is, you and I approximate the system as linear time invariant, causal systems, and then derive governing equations which are in the form of linear ODEs with constant coefficients and so on, and then we get the transfer function, right? So the point is, we make a lot of assumptions in the formulation, and then we essentially come up with the notion of transfer function and poles and so on, right? But in real life, as we know, we are going to have unmodeled dynamics. You and I may not have considered some effects. There may be parametric uncertainties also. So even let's say, if we consider this example, we may model some structure as a mass spring damper system. We will be assuming some nominal values of C and K But in real life, that C and K may vary around a nominal value in a band. That is, we may have C naught and K naught. K naught can be varying between K naught plus or minus delta K, and C naught may be varying around some delta C, right? So that is pretty much going to happen, right? So even let's say we use our automotive suspension as a keep on utilizing the vehicle, right? The spring and the shock absorber properties which are used in the suspension will vary with them, right? Slowly. So obviously, when such uncertainties, disturbances, parametric variations, and all come in. Okay, so this is what is called as a parametric variation. Okay, so when the model parameters change with time and so on, when compared to a nominal one, it may so happen that the poles in the lifetime of a system may be around a region around the nominal location. So these are the nominal locations of the poles. Okay. So, but then with time, due to whatever unmodeled dynamics or parametric uncertainties or you know like you know like essentially disturbances that may come in, we may have a band around this nominal value, right, in which the pole may lie. Okay, and this band depends on this region depends on the system. Okay, now if you look at system 1 and 2, the nominal system is stable. Okay, that is because why? The poles, both poles are nominal poles are in the left of complex. And from a response perspective, do we want poles to be closer to the imaginary axis or away from the imaginary axis?
Sir, which is close to imaginary axis is the more dominant
So,
pole.
more dominant pole, and that will in fact result in better response characteristics, right, in terms of settling time and so on, right? Correct. So, in fact, closer to the imaginary axis, the transient response will be better, right? So, the point is the following, right? Although S1 and S2 are both stable, right? And like both S1 and S2, the poles are the left of complex plane, and S1, has more dominant poles than S2, right? The issue is, as we have parametric uncertainties, and let us say, suppose there is a scenario where the band of poles may exceed, what to say, a certain bound, and the poles of S1, let's say the bound around the nominal location is such that there may be a risk of this nominal pole going into the right of complex, although the nominal system was stable. Okay, then we have an issue. Okay, so both systems S1 and S2 to begin with were are what are called absolutely stable. That is what is called absolute stability. But from this argument, we can immediately observe that S2 is going to be relatively more stable than S1. I hope that point is understood, right? So what is relatively more stable? That is in the presence of disturbances and parametric uncertainties, due to the fact that the poles of system S2 lie further in the left of complex plane, there is a lower risk of those poles even getting close to the imaginary axis than S1. Okay, and so that is why S2 is relatively more stable than S1. Okay, so that is the notion of relative stability. I hope that is clear. So what we been calling as stability till date, to be a little bit more finer, in today's class we are calling it as relative stability. Okay, so that's what we have. Okay, and the point is, if we look at how do we evaluate metrics that give us idea about the relative stability of a system. Once again, we go back to the closed loop characteristic polynomial and closed loop characteristic equation, which is 1 plus g of s h of s equals 0. Okay. So when a pole process from the what to say left of complex plane to the right of complex plane, obviously it needs to pass through the imaginary axis, right? So when it passes through the imaginary axis, what is the value of S? S is of the form j omega, right? So when we substitute S equals j omega, we get gj omega hj omega to be equal to -1. Okay. So what is the physics behind this equation? Gj omega hj omega is -1. It is the, please recall, g of s h of s is the open loop transfer. So gj omega hj omega is the open loop sinusoidal transfer function. When that becomes equal to -1, we know that there's a migration of a pole from the left of complex plane to the right of complex plane. Okay. So this becomes very important. Okay. So the -1 point in the complex plane, as we know, has a magnitude of 1 and a phase of plus or minus 180. We will take -180 because we are dealing with causal or proper transfer functions, right? So that's why we are taking -180 here. So the -1 point has a magnitude of +1 and the phase of plus or minus 180 degrees. So the way to interpret this equation is that given any system which is initially stable to begin with, the question is how close is the open loop sinusoidal transfer function to the -1 point. Okay, then that essentially captures the relative stability of the system. Okay, so the open loop transfer function is not going to go through the -1 point, but then what we are asking is that how close is it to the -1 point? And why are we worried about the -1 point or interested in the -1 point? Because the poles will cross the imaginary axis when g of j omega, h of j omega becomes equal to -1. Okay, so that the closed loop poles will cross the imaginary axis. Okay, so this equation becomes very important. So now, once again, the importance of the open loop transfer function becomes clear, right? So you remember when we initially started definitions of the various transfer functions, I told that open loop transfer function g of s h of s is a construct, but then it's a useful construct. By now we have realized, right? It is used in the root locus, it is used also in frequency response, it is used in relative stability and so on, right? So it has multiple applications. Okay, so now if we look at corresponding parameters that we define what is called as a grain crossover frequency, omega g. Okay, so omega g is the frequency at which the magnitude of the open loop transfer function becomes 1. Okay, these are all definitions, please note. Okay, so I will explain the physics shortly. Okay, then phase crossover frequency, it is the frequency at which the phase of the open loop sinusoidal transfer function becomes -180. Okay, so that is the phase crossover frequency. Okay, now having ascertained these two frequencies, if I calculate what is called as gain margin, which is the reciprocal of the magnitude of the open loop transfer function, sinusoidal transfer function at the phase crossover frequency, I get what is called as a gain margin. Why is this gain margin important? Suppose, let us say I have the open loop transfer function, right? It needs to pass through the -1 point. So there are two ways I can evaluate it, right? So there is how much should I scale at omega p. Okay, that is, I have some magnitude of the open loop transfer function at the phase crossover frequency omega p. The question becomes how much should I scale it at omega p to make the magnitude as 1. Okay, and that is the gain margin. So if I have large enough gain margin, that I know that the system is relatively stable, because if I have disturbances, the magnitude of the transfer function, right, is not going to change a lot, right, or it's not going to come to 1 very easily. Okay, so that gives me a lot of cushion. Similarly, the phase margin is calculated at the gain crossover frequency. So you can see a nice symmetry in the calculation or the definitions of these two measures, right? So the gain margin is calculated at the phase crossover frequency, and the phase margin is calculated at the gain crossover frequency. Okay. What is the phase margin? We figure out the phase of the open loop transfer function at the gain crossover frequency. This is going to be a negative number, and we figure out what should be the phase I should add to it to make it go to minus 180. Why minus 180? Because how much phase that should be given at omega g, because at omega g already the what to say, the the magnitude of the open loop transfer function is 1. So now if I have to make the open loop transfer function go through minus 1, the magnitude is already 1. So I need to make the phase go to minus 180. Okay, so that's what we have. All right. So essentially the phase margin means, I figure out the phase which will ensure that the phase of the open loop transfer function goes to minus 180 at the gain crossover frequency. Okay. So we want gain margin and phase margin to be as high as possible. Of course, positive numbers, and also like as high as possible, so that we ensure that we are far away from the minus 1 point as far as the sinusoidal open loop transfer function is concerned. Okay, so that is the idea of having these metrics for relative stability. Okay, so once again, let me recap. What is relative stability? We want to figure out how stable is the stable system. Okay, that is, we have a nominally stable system to begin with. You and I are asking how stable is my stable system. Okay, so consequently, when we have relative stability, we have initially system to be stable, the poles to be in the left of complex plane. And when we have perturbations, these poles may migrate to the right of complex plane. The question that you and I are asking is that, like, how tolerant is the system to this? Okay. So for that, we once again look at the open loop.
Sir, I have a clarification to ask over here, sir. I'm sorry. Can I ask, sir?
Yeah, please go ahead.
Sir, when you said that it's a relatively stable system, okay, it's relative stability you are talking of at the moment, and you have told that in the nominal condition, when the plane, roots are lying left of the plane, okay, sir, then system is nominally stable in that sense. But you again you use the word. Suppose if we give some perturbation and it becomes it comes to an unstable zone, right, sir?
What is the question, Roshan? Do you want me to repeat the explanation?
So the question is, sir, here is that the perturbation is basically because of the deterioration of the system, and hence the property of the system is getting impacted, not because of external forces or something like that, right?
No, not external forces, Roshan. It's because characteristics of the system may change. That's why I gave an example of the automotive suspension, right? Let's say, you fix a spring and a shock absorber, right? You assume some norm in the car, that's going to change, right? So that's a perturbation in the parameters, right? It's not a perturbation in the input sense, right? That is why I wrote it as parametric variations. That is one reason why such a response may come, right? Such variations may come. And other reason may be that, see, suppose even when you model the suspension, you and I modeled as a mass spring damper system. Like that's an approximation, right? So you and I would have missed some, dynamics, right, in the approximation. So all those things can create issues. That's what it is.
Right? So just to clear my understanding further, sir, just I want to ask one question. Imagine that the system parameter is infinitely stable, like there is no change of characteristic of system parameter with the time. So in the first place, if I design a system and if the roots of the roots of the system is lying on the left side, so whatever perturbation we give, external perturbation we give in the system, it will not move to a stable zone. Is that right, sir?
Okay. Let me maybe if I accidentally use the word perturbation, I withdraw it. I'm sorry.
I'm
So
sorry, sir.
what I meant by perturbation, no, Roshan, I think it's very important. Thank you for alerting me. See, when we talk, I don't know, maybe sometimes I use the perturbation in a certain sense in my mind. Like I didn't mean by perturbation a force, right, or an input, right? Let's say, like we have a simple pendulum, I tap it, right? That is a perturbation, right? So what I meant was that if I accidentally use the word perturbation in this discussion, I meant variation in parameters. Okay, so that means you have a nominal system with a spring, let's say, of 100 Newton per meter stiffness, right? Let's say it can vary between 80 to 120. That is the variation I am talking about. Okay, yeah.
So just only one clarification I
Ah,
wanted.
ah.
Like, suppose if the stiffness of a system is 80 Newton meter for spring constant, and there is no deviation allowed from that value. So
Mhm.
even considering that stiffness value, if my system is marginally on the left plane, so no matter whatever force I give to the system, it will remain
Ah,
at a
yeah,
stable level
yeah, yeah.
only.
See, stability is independent of the input that you give, right? Once the system is stable, it is
Yes.
before stable, right?
Right,
Yeah.
right.
All
Thank you.
bounded inputs, you will get bounded outputs.
Fine,
Point
sir.
done, right? But the point that you and I are articulating is that it is very difficult to get a perfect system in the real world,
I
right?
got the point, sir.
So,
I got
yeah.
the
So that is the entire point of this discussion. And that is why in today's class, I introduced the adjective absolute before stability. So, see, we have to introduce terms at the appropriate locations, right? So, if I started using absolute stability from the first class, we would be puzzled why it is absolutely stable, right? So now we get the point, right? Suppose if we had a perfect system, like no perturbation, no deviation in the nominal position, the system is absolutely stable, right? So, yeah, and then the point is we have, like, variations in the parameters. Then, if at all there is a potential, I'm not saying it will always be, okay? If at all there is a potential for the poles to migrate into the right of complex plane, then the system tends towards instability, right? That's what you and I are capturing through relative stability. So the question that you and I are asking, Roshan, is that how stable is the stable system? Okay, so I hope the two words stable are interpreted in a proper way. That is, you have a stable system to begin with. How stable it is, right? What is the degree of stability? Okay. Okay.
So thank you, sir. I'm sorry for for silly dot I have
No,
asked.
no, no.
That's
I
what.
think this is very important. It's very important for me to clarify. Thank you for the question. Nice. Okay. So, what is the degree or measure of stability? Okay. So that's what we have done by considering the closed loop characteristic equation and then like defining these gain crossover frequency and phase crossover frequency. What is the motivation for these? Once again, if I had all the closed loop poles to be in the left of complex plane, if the closed loop poles migrate to the right of complex plane, they have to do so only after they pass the imaginary axis, right? That is the concept we are using. And when they pass the imaginary axis, g of j omega, h of j omega becomes -1, right? From the closed loop characteristic equation. And -1 point can be divided into two parts, right? What to say, magnitude being 1 and the phase being -1. Okay, so that motivates the definition of gain crossover frequency and phase crossover frequency. Under the phase crossover frequency, we calculate the gain margin. At the gain crossover frequency, we calculate the phase margin. Okay, so that I hope that sort of like the symmetry is also clear, right? Why do we calculate it? Because we want to figure out how much positive gain I have at the phase crossover frequency, which will ensure that my system doesn't cross over, and phase margin gives me how much phase I have before I hit the -1 point when the magnitude is 1, right? Which is the gain crossover frequency. Okay, so these parameters give us measures of relative stability, right? So I hope that point is understood. All right. Okay. So let's do an example so that we can understand it better. So suppose, let's say we consider the system with an open loop transfer function 1 divided by s times s plus 1, then if you and I calculate the closed loop characteristic equation, this is the closed loop characteristic equation, right? So immediately I can conclude that the closed loop system is absolutely stable. How can I conclude that s squared plus s is equal to
All coefficients have same signs.
very good, right? So please note that it's a second order polynomial. All coefficients are non-zero and of the same sign, right? So that's why the closed loop system is absolutely stable. Now, what we do is that, like, we figure out the sinusoidal open loop transfer function, which in this case is 1 by j omega times j omega plus 1. The magnitude, you and I know how to find the magnitude by now, right? This is going to be 1 divided by omega, and then the magnitude of 1 by j omega plus 1 is square root of omega squared plus 1. Okay, so we have this, and the phase is going to be minus 90 minus tan inverse omega. Okay, so that's what we have for the phase. All right. So now when we want to calculate the gain crossover frequency, we equate this magnitude to be 1. So we have, this magnitude to be plus 1. And then, like, we solve for omega g. When we solve for omega g, we get two roots. Okay. Of course, we get a quadratic equation in omega g squared. Okay. And then we solve for omega g squared first. We get two values, 0.618 and minus 1.618. Why have I crossed out minus 1.618? What do you think is the reason?
Because omega cannot be this thing, sir, negative. No?
Omega squared cannot be negative because I have to take the square root to get omega, right? Omega g in physical sense, it's an angular frequency, right? It has to be a real number, right? So now if I take square root of a negative number, what will I get? I will get
imaginary number, so it's not
imaginary
possible.
number. So that is why we have crossed out 1.61. I hope it's clear, right? Sorry, minus 1.61. Okay. So then omega g will be square root of 0.618, which is 0.786. Okay. Now let's calculate the phase crossover frequency. The phase crossover frequency is essentially what is the frequency at which the phase becomes minus 180, or the phase of this transfer function is minus 90 degrees minus tan inverse omega p. That should be minus 180, or tan inverse omega p should be 90. When do you think the tangent of tan inverse of a variable goes to 90 degrees? What is tan 90? It's infinity, right? So consequently,
Infinity, yes.
only when the argument is infinity, the inverse will be 90 degrees. So what it means is that the phase crossover frequency is infinity or tending to infinity. That is, for this particular system, this is a positive point. That is, the phase of the open loop transfer function is going to go to minus 180 only when omega tends to infinity. Like that means practically never, right? So that is a positive point for us. So consequently, you will see that we have infinite gain margin, which is once again a very good open loop sinusoidal transfer function at omega p and take its inverse. The magnitude of the sinusoidal function, open loop sinusoidal function, is 1 by omega times omega squared plus 1, right? So what do you think will be this magnitude? Sorry, this should be omega p. Okay. So omega p tending to infinity. What do you think this value will tend to?
0, sir.
It will tend to 0, right? Because denominator will tend to infinity.
Yeah.
But then we are looking at the reciprocal, right? Gain margin is 1 divided by this thing, right? Then what will that tend to? It will tend
Infinity.
to, right? So that is why we get infinite gain margin, which is very positive, right? So what it means is that, like, doesn't matter how much ever gain I put into the system, I'm never going to reach instability. So then we go and figure out the phase margin. For that, we figure out the phase of the gain crossover frequency, which is minus 90 minus tan inverse omega g. Then I add 180 to that. Okay, so omega g we substitute as 0.786. If we do the algebra, we will get the phase crossover frequency as 52 degrees. So what it means is that due to some reason, if there are lags in the system, as long as the lag which is added is less than 52 degrees, I'm fine. Okay, I'm not going to reach the limit of instability. Okay, but however, when the lag reaches beyond that, I may become unstable. Okay, so that is the outcome. Okay, or the inference that you and I can draw. Okay, so I hope the calculation of the gain margin, phase margin, and the two crossover frequencies are clear, right? So any questions on this concept?
Sir, phase margin concept, please. It is. I could not comprehend it, sir. Please explain.
What it means physically, Roshan, is that like let's round it off to 52 degrees, for the sake of talking, right? 51.83 to 52. Now, let us say there are lags in the system, right? Due to whatever reason, let's say the friction increases, right, in the system and so on. So the system becomes slower, right? Due to whatever reason that may come in practice. When the system becomes slower in response, as long as the phase of the its nominal open loop transfer function does not deteriorate by more than 52 degrees, which is a significant measure, I will not reach the crossover. Okay, so what are we looking at? The question that we are asking is that when will the nominal pole cross over into the right of plane, right? So in this particular example, if I keep on adding gain, okay, through some mechanism, I will never cross over. Okay, so that is the concept. Okay, but then if I essentially add phase lag, if I add up to 52 degrees, I'm okay. But beyond that 51.83, I will go into instability. Okay, so that is how physically we need to. Okay. All right, I hope that is clear.
Sir, is there any limit set as means to say that this much margin is great? Means for gain margin, it is understood that infinite margin is the best. But so for phase, it should be what values?
Once again, the designer specifies because like it can be sometimes people will say I want phase margin of 30 degrees or 45 degrees. So okay, so that so around that ballpark is what typically people will.
Sir, just to suppose you have told sir if the phase lag is more than 52 degrees, then system will be unstable, right, sir?
System will cross over into the imaginary axis and go to the flow. The poles.
RHP, right, sir? Yeah. Sir, if you can just draw it graphically, sir, and show it, sir, a bit. I'm sorry for asking this.
Graphically means in what?
What I meant to say, sir, if you go to the little bit up, sir, that sense, please.
Yes, please.
Now you have like more up. So here the S1. So suppose if I'm adding like phase lagging to this, like how to after suppose 90 degree I have added. So that means how it will convert to the new point in the
so please note Roshan, what will happen is that when the phase lag is added, the transfer function characteristic itself will change. Okay, I can intuitively understand your question, but there is no simple schematic to demonstrate it. Okay, it is just that like with system deterioration, it may become slower. That is why I brought that engineering word slow, so that you and I can understand it from a broad sense, right? So it will essentially deteriorate in performance, and when the phase becomes phase lagging means broadly you and I can understand that the system is becoming slower in response. Okay, when that phase lag in fact is a negative quantity. Okay, when we say phase lag, we can use a positive quantity. When the phase decreases by more than 52 degrees here, then we have a problem. Okay, so we have the poles, right, closing over into the from the left off into the right off context. Okay, so I think once again, Roshan, I can as I told, I can intuitively understand that your question, but I am not aware of a very simple schematic which graphically explains this. Okay, we need to picturize it in our mind. And when we do design examples, you will be able to picturize it using Bode plots. Okay.
Thank you, sir. No. Thank you. Understood.
Yeah, thank you. So the last, what to say, definitions in this class is that like when we did performance specifications and did group locus and looked at unit step response, you and I used parameters like rise time, settling time, peak overshoot, and so on, right? So when we have those parameters for unit step response, the corresponding question is that like what are the performance specifications when we use like steady frequency response method, but there are controllers called lead compensator, lag compensator, and all. Once again, you can watch those control systems videos where I have explained that. Okay, and then when we do that, this phase margin and all will become even more clear, right? So I have not gone into the details in this particular course, right? Okay. So when we want to do design using frequency response methods, the corresponding performance specs are gain margin, phase margin, which we already learned. Resonant frequency, resonant peak also we already learned. But then we also have what are called bandwidth and cutoff rate. So what are these? So we calculate the closed loop transfer function. We plot the magnitude plot of the closed loop transfer. Okay, please remember this is a closed loop transfer function. Typically, the low frequency asymptote will be 0 decibels for the closed loop transfer function because it's stable. Okay, and then what we do is that like we figure out at what frequency the closed loop transfer function reduces by 3 decibels. Okay, from the 0 decibel value. Okay, so and that frequency is what is called as a cutoff frequency. Okay, so cutoff frequency is a frequency at which the value of the closed loop sinusoidal transfer function, right, decreases by 3 decibels when compared to the zero frequency value or the low frequency value. Why this 3 decibels? Okay, so 3 decibel, in fact, corresponds. Or let me leave. What do you think is the significance of this 3 decibels? Do you know from signals? Any guesses or ideas? Okay, so please find out. Okay, so it will be good to find out this. Okay, so what is this 3 decibel corresponding to? Okay, so please do find out. But that is the definition of the cutoff frequency, and the bandwidth of the system is the region from 0 to W. Omega c. Okay, so system will allow to pass. Okay, the frequencies which this closed loop system will allow to pass. Obviously, we want high bandwidth systems, but high bandwidth systems are costly. Okay, they are going to be expensive, so that's why there is always a trade. Okay, cutoff rate is also the rate at which this slope of the magnitude curve goes at the cutoff frequency. Okay, so that is the slope at the at omega equals omega c. That is cutoff frequency. Oh, okay. I have already given part of the answer here. Okay, I didn't even realize it. Minus 3 decibels correspond to 1 by root 2. Okay, now you can figure out why. Can you now guess what is 1 by root 2 and what is its significance from signal perspective?
Sir, read 0.707. So basically, am I audible?
Yes, please go ahead.
Yeah, so 1 by root 2 is 0.707. That
Okay.
means we are going to increase or decrease by that reduction in the signal voltage will decrease by that amount, right? So,
see the what will be the square of 1 by root 2?
Sir,
RMS value, sir, root mean square.
Yeah.
So half the
half, right? So now,
half.
we have almost come to the answer, right? So typically, the quote unquote power of a signal, right, is going to be proportional to square of the magnitude, right? So when we have the signal decreasing by 3 decibels, that means its power is halved. So in a sense, what we are saying is that like at omega c, for input frequencies beyond omega c, the corresponding power of the input signal will be half or lower, right? When we compare it to frequencies, less than omega c. Okay, so that is the answer. I hope it's clear. Okay, why is minus 3 decibels? Okay, yeah. All right. Okay. So, any questions on what we learned? And I will quickly give a recap of where we are. Like as Prem asked at the beginning of this. So, this is a nice transition point for us also to have a recap. So, because if you look at it in this course, we are dealing with automotive control. As we know, we wanted to do classical control. To begin with classical control, then we have what is called modern control. What was classical control? What was modern control?
Classical control is basically done through transfer function, and then like what I'm just deciding the poles and zeros, positioning them on the plane. Whereas modern control is basically more dealing with state specification and modern
Time domain.
Time domain.
So
Very good.
classical control is complex domain, whereas modern control is time domains.
Very good. Okay. So now you can see that next class onwards, tomorrow onwards, we will start state space. Okay. So we learn modern control. Okay. But what have we learned till now? Okay. In classical control, we have learned the framework of classical control. What is the closed loop control system? We have learned about PID control, right? We have learned about stability and performance criteria. Sorry, what happened here? 1 minute. Sorry about that. I think the software Adobe Acrobat also has become too smart. Like it is converting automatically. So stability and performance metrics or criteria. Then we learned about control design using like the routes criteria, so that like you and I can get bounds on the controller parameters. Then we also looked at the root locus to figure out regions of the controller parameters. Then we looked at frequency response, right? Where we looked at the Bode plot. Okay, the Bode plot helps us in experimental determination of transfer function. Okay, so you have done all these things. And now comes the question. Like here, one may be wondering. I'm sure. Even one may ask the question, hey, why did we learn so much theory and math and so on? As I told you, the first project will involve all these items. Okay, so the first project that you will do will be on brake control, where we will give you data. Okay, and then you will use the ideas from Bode plot to figure out the transfer function, and then use the transfer function approximation to design controls, right? And then plot the root locus, evaluate for stability and performance and so on. Okay, so you're going to utilize it for an actual automotive case study using all these concepts. Okay, so I hope it's clear where we are. Okay.
Sir, one thing I want to ask you is asking that after reading whole Ramayana, who is Lord Ram? That type of question is this, but still I'm asking, sir. I'm sorry for that. Frequency response, sir. Basically, we are giving the input as sinusoidal, right, sir?
Yes.
Why it is so, sir? I'm sorry for this very silly question.
That is the definition of frequency response, because see, when we give impulse, we call it impulse response, step response also, right? Why, when we call sinusoidal, when we give sinusoidal input, why not call it a sinusoidal response, right? So it so turned out that there is a history that we need to respect, Roshan, right? Because if we look at it, the sinusoidal input is characterized by frequency, right? Sin omega t and cos omega t, right? So that is why people call it as frequency response. That is one answer. And the second reason, right, is that as we already learned, for the class of systems that you and I are studying, right? When we give this sinusoidal inputs, the steady state output is also a sinusoid of the same frequency. So in a sense, frequency becomes very important. Okay, so that is why we call it as frequency response. I hope that broadly answers. The
Yes, sir, I got it. Thank you. Thank you so much, sir.
So, and
Thank you,
Prem,
sir.
I hope the big picture view is clear, right? Where we are, you know.
Big picture view is clear, sir. Am I audible?
Yes, please.
Sir, big picture view is clear, but there is a macro picture view doubt that we have today. Can we ask that also?
Which one? What is it? No.
Sir, it's related to root locus. So,
Yeah, please go ahead.
Sir, can we have the root locus procedure PDF open? I'm sorry to ask if it's possible.
Procedure video means that Google Drive file, is it?
Procedure PDF, sir. That root locus PDF. Step by step of root locus PDF.
On the Google Drive, right?
Yes, sir. Yes, sir. So on the fourth point, there is a doubt.
Okay.
So there is a breakaway and break-in point. So there are two questions in this. Two consecutive open loop poles are zeros. Technically, we should have two consecutive open poles. If there is a zero between two poles, for example, k into s minus 2 divided by s minus 1, s minus 4, in that scenario, I mean, does the equation not break even?
So I will draw and demonstrate. Okay, this is only one of the conditions. Okay, so this is not the only condition for breakaway or break-in point. So what happens is the following, right? Let's say we have the real and the imaginary axis, right? So let us say we have this, right? So there is a probability that there is a breakaway point. Please note, when we had this system for positive k, there is a breakaway point, right? For negative k, there was no breakaway point, right?
Yeah.
Because the branches went in different directions. So I want to give a very qualified answer, right? So now the question is, what happens if we have a zero in between, right? Then very unlikely that we will have a breakaway point, but once again, you and I need to ascertain things. Okay, so what may happen is that like one of the branches may go to 0, 1, 0, and then n, and another branch may go to infinity along the asymptote. Okay, in such a case. Okay, now for the sake of argument, let's say I put two zeros like this, right? Then can there be breakaway or break-in point? Right. Once again, it depends, right, on the value of k and the type of feedback that we are considering. Okay? So what I'm trying to convey is that like what I wrote in the document is only one probable scenario, okay, not the only scenario, okay, and not necessarily always the scenario. I hope I have sort of like broadly answered the question, right? The best way to, the surefire way of figuring out breakaway break-in point is to solve that equation. Okay, what we learned. B prime is A of s minus B of s A prime is equal to 0. Find all the values of s and then like calculate the value of k at those s and then go forward from that. Okay, so that is the best way to deal with this. Okay, yeah.
The next point is breakaway. Logically, when two poles, we are operating between the two poles, then it is breaking away from the intersection point and it's moving in the, along the imaginary axis. How do we connotate break-in point for the zeros? We could not visualize the break-in.
Yeah. So once again, let's say I am only taking two zero. What did we learn in root locus? We learned that if there is an open loop 0, each branch of the open loop 0 must end at a sorry, each branch of the root locus must end at an open loop 0, right? Point 4. I hope that is clear, right? Is that understood?
So essentially what we are telling is the root locus will start from a pole and it will go to a 0.
If there are zeros.
If there are zeros,
it will go to asymptotes, right? So the premise to the answer is that I hope all of us understand that if there are open loop zeros, then one branch will end at each open loop 0. Is that understood? Right? Yeah. Now let's say we have a cell axis without anything in between. Now let's assume that it's going to end like this. Of course, it can also come the other way around, right? It can come like this and then end. It can come like this and end. Then there may not be break-in point. But then let's assume this particular case. Then what will happen is that if I keep on extending it, they will intersect somewhere and they should have come in from somewhere, right? Otherwise, how will I end up here? I hope it's like an origin and a destination, right? This is the destination, right? So the origin has to be somewhere, right? Is it not? The origin comes from somewhere in the imaginary axis or some other place, and the two branches intersect on the real axis, and then that is why it is called as a break-in point. Why is it called a break-in point? Because after hitting this point, they break into the real axis, right? They go along that real axis, right? So that's why it's called as a break-in point. Right?
Sir, imagine we have a situation wherein, let's take the example that you have plotted above. How will the because understanding is it should come from an imaginary axis and then move towards the zeros.
Yeah.
In example that you have plotted above, we have zeros and poles on the real axis, so it will directly go from pole to 0. In the real axis itself, or it will go to imaginary and then will come back.
So I just draw an incomplete example. Let us say we have something like this. Okay. So then what will happen is that you may have two branches starting like this. They may hit. Okay. Then one may come like this, right? And then it may go in. The exact shape depends on the transfer function. Okay. So your good name, please. I'm sorry.
Keshav.
Right? So Keshav, the exact shape may depend. Okay. So you may have a breakaway point like this, and finally you may have a break-in point also. Some asymptotes like this. Okay.
Yeah, fine.
So once again, we need to work out the real transfer function. So I'm only explaining the concept. Okay. So when we work out the actual case, from the real system's open loop transfer function, we'll be able to generate all these things and also understand it. Okay. So I hope all of you worked out the homework problems, right? So that would have provided.
So when we are doing that homework, only these doubts are popping up. That's the reason why.
Okay. So essentially, this is all this, and you can certainly ask more questions tomorrow also. Okay, so tomorrow we can spend time answering questions also, right? So that your preparation for the midterm exam is okay.
Sure, sir.
Yeah, yes, sir.
Got it, sir.
Yeah. Okay, so I think it's almost time for your next class. Arunachal, is anyone present today? No,
sir, only 1% absent, sir. Rahul.
Okay, fine. All right.
Okay, sir. Thank you.
So we will continue tomorrow. Maybe what we can do is that tomorrow we can start with questions, okay, rather than just jump into state space representation. If you have any questions on what we have learned till now, and also
there are a couple of questions which is unanswered. Maybe we can start with that tomorrow.
Yeah, no problem. Right. So whatever you feel are unanswered, we can start with them, and you can also think of more questions that come.
Noted, sir. Thank you so much.
Okay. Thank you. See you tomorrow. Bye-bye.
Thank you, sir. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.